page, we're going to be talking about the free body diagrams that go with circular motion. And so just as we did free body diagrams early in the year, we need to go back and remember that. So for instance, I have these little things set up, and you can do your best to draw the circles and what have you. But we have a ball suspended from the ceiling, and it's swung in a horizontal circle. So in other words, there is a ball hanging here. It's hanging from a string that's attached to the ceiling, and it's being swung around. You can kind of think of it like a tether ball on the recess playground. So you have this tether ball going around and around and around, but we are concerned about the free body diagram for this. That's my diagram of like what's going on, so you can see what's going on. My free body diagram is just the ball itself, and what does it have going on? Well, it has the force of gravity, which is supposed to go straight down. My line was a little crooked. And it also has this force, which is the force of tension. Now we need to talk about centripetal force. Centripetal force is always pointed inwards. And so if I draw my free body diagram, I'm not going to put it on there. But on the AP test, they don't want you to put components on your free body diagram. So technically we are done with our free body diagram. But the whole point of this worksheet is to say, what is a centripetal force? So the centripetal force is this vector right here. It is not its own vector. There is something causing this vector. What is causing this vector? Well, really, it's just a component of the tension. So I can see that my T didn't really come across. That's a T. That's the force of tension. So in this case, my centripetal force is really the force of tension in the x direction. It's not its own force. It comes from something else. It always comes from something else. It's never its own force. Okay, what if we have a ball on a tabletop? And I'm trying to think. There used to be these things. Do you remember these things you would put on your ankle when you were a kid and you like swing it around and jump over it? I can't remember the name of it, but that's what I'm imagining. Or maybe like a spinner of some kind. So anyway, we've got this ball and someone is swinging it around in a circle on a tabletop. What's the free body diagram? Well, of course we have the force of gravity. And in this case, we have a normal force. Now, on the other one, we didn't have a normal force because it was not on a surface. It was on a string, and the string has tension. But if it's on the surface, it has a normal force. Then there is something that is causing it to go in this direction. There is always something to do that. And so that's our centripetal force. But the question is, where does that centripetal force come from? It's not its own force. It's not just like, here's a centripetal force. It has to come from something. What does it come from? Well, in this case, it comes from the tension on that string. So in this case, our centripetal force is coming from the tension on the string. Notice there's nothing balancing it because it's not going in a straight line. It's not a balanced force. It is an unbalanced force, because that's why it's going in a circle. Balanced forces go in straight lines. Okay. Now we have a person who's swinging a ball around and around and around. Or imagine you have your keys on a lanyard and you're swinging them around and around and around like this. So now we're like looking straight on, not on the tabletop, but just like this, like the person is behind there. So here we have the ball and it's at its highest point. So what forces do we have? Well, we have the force of gravity, of course, and we also have the force of tension. And so in this case, on number 3, our centripetal force is actually both the gravitational force and the force of tension. And just because I'm going to compare it to other ones later on, if I solve this for tension, then that would be the centripetal force minus the gravitational force. What if it's at its lowest point? Then what? Well, we have our gravitational force going downwards, as we always do, but now the tension is going the other way. And so now the centripetal force is equal to the force of tension. And that's where the centripetal force is coming from. At this point, this ball is going to have more tension on it than it does here. Like imagine, I think you can imagine, but we'll do it in class too. If you're spinning this around, when it's at the top, it's kind of slack, right? But if it's at the bottom, you're having to really pull it to make it go around. And so that difference is because in this case, up here, we were subtracting the centripetal minus the gravitational to be the force of tension. Whereas in this one, the force of tension is actually the centripetal plus the gravitational. I guess you should write over here, we should write minus F sub g. And so then when we solve that, our tension becomes the centripetal plus the gravitational. So that's a larger force than this one, which is getting subtracted. Okay, so number 3 was at the top, number 4 is at the bottom. What if it's halfway? Well, we always have our force of gravity working downwards. And we, of course, here we have our centripetal force, which is also our tension. There is no other force in the x direction. So in this case, the centripetal force is the force of tension. These next two, I just don't like these questions. They're kind of confusing. So let's just not do those. And back to these 3, the top, the bottom, and the side. In this class, that's really all we will do. We won't, I don't think, I might end up eating my words, but I don't think we're going to do ones that are like at odd angles around there. I think it's just going to be the top, the bottom, and the sides. All right, you are in a car and you're making a turn. What is keeping you on the curve? Why aren't you flying off the curve? What is keeping you there? Well, first let's draw our free body diagram. We have the force of gravity, of course. We have the normal force. Then the question is, what is this? Something must be keeping you on the road. Otherwise, you would have flown off the road. Why didn't you fly off the road? Because there's friction. The friction in your tires is keeping you on that road. So in this case, the force of friction is causing it to stay on the road. It is the centripetal force. Now, I don't know if you know this, but cars in NASCAR, they don't have very much friction. Why not? Because friction slows you down. They don't want to be slowed down. So, I didn't know how to draw this one. This one is kind of wacky as far as the drawing goes. But if we have a car making a turn on a banked turn, in fact, I don't like this drawing at all. I didn't like the drawing that I had there. Let's start off just with a car. It's on a banked curve. So, for instance, let's say the road, it is at an angle, and maybe you've seen that. Like this is the wall, and this is the car. The road is at an angle. Well, why is that? So let's talk about that free body diagram. Well, the free body diagram says, of course, we have the force of gravity going straight down. Now this time our normal force is not going straight down. Our normal force is perpendicular to the road. So now the question is, what is causing the centripetal force? And maybe you can see that the centripetal force is coming from the bank. So I didn't draw it perfectly well. I tried to. It would be from the normal force in the x direction. So we would break up this vector, the normal force vector, break it up into components, and the x component of that is going to be the source of our centripetal force. We have a roller coaster going over a hill. Of course, we have the force of gravity. We also have our normal force. That track is providing a normal force against the cart. What is providing the normal or the centripetal force? Well, in this case, the force of gravity is providing the centripetal force. And you better hope that the force of gravity is greater than the normal force. Why? Because if it's not, it's going to go launching off the track, and we don't want it to launch. So we want it to stay down here, so we're hoping that the force of gravity is greater than the normal force. Okay, on this one, we don't have as much concern about flying off the track because we just know we're not going to because we've got so much gravity here, we're okay. But in this case, the normal force is causing the centripetal force. That's that normal, that pushing up against the cart is creating it, causing it to stay there on the track. I'm going to go back to number 10 for just a second, and I'm going to say that kind of like we did over here with 3 and 4. It is the gravitational force, but we have to account for the fact that there is a normal force. So in this case, the centripetal force really should be the gravitational force minus the normal force. And again, the gravitational force better be bigger. That's what's causing it to stay on the track. But this might be a better equation. And similarly for number 11, that we might say that the centripetal force is actually the normal force minus the gravitational force. That might be better than these two equations. Okay, a satellite is orbiting the Earth. I don't know if you know about satellites at all, but let's say here's the Earth and here's my satellite. What is keeping it going in a circle? Why isn't it just floating off into space? And the reason is gravity. The force of gravity towards the Earth is what's keeping it in orbit. So the centripetal force is the force of gravity from the Earth. Okay, not the greatest drawing in the world, but the Finnish fling at Worlds of Fun, which I don't know if you know, but it's gone. So, but the way it used to work, I never rode it because it would make me sick. You stand against the wall, and it spins and spins and spins and spins, and pretty soon they drop off the floor. That's my understanding of the Finnish fling. Couple of questions. What is causing the centripetal force? And also, next question, what is causing the person to stay? So here's our person. They have the force of gravity. When we remove the floor, that's gone. We don't have a force there anymore. So I can't draw a normal force. That floor is gone. But I do have a normal force this way, the wall pushing against you. And so in this case, the centripetal force is coming from the normal force of the wall pushing against you. There's a vector I haven't drawn yet. What's keeping you up? Because right now, this gravitational force says you're going to fall down. Why aren't you falling down? There must be a force acting in this direction. Oops, I don't want it to be normal. And so what is the force acting that direction? It's the frictional force. All right, we will be using our skills of free body diagrams quite a bit in this unit, so hopefully this is a good introduction for you of those free body diagrams.